Good morning, class. Welcome to online classes of Metallurgy and Material Sciences. Today we are going to see the lecture 4 of Metallurgy and Material Sciences. The topic is about work hardening. First of all, let us see what is work hardening. Next, we will discuss about recovery, recrystallization, and then we will further go to next topics like mechanical properties of the material. So let us see what is work hardening. Work hardening is nothing but a strengthening of metal by plastic deformation. So this strength is generated because of dislocation density. So we have already seen that the dislocation is nothing but the line defects which propagate in the name of slip. So it moves from one point to the other point. I have already told that this dislocation will sometime lead to reduce the strength of the material, but whereas if the density is more and it is concentrated at some point, it will create the disturbance to crack the material, which further increases the strength of the material. So work hardening is also called as strain hardening or cold hardening. So I can tell you an example, like if you take a material, if you are stretching a material, you leave the material after stretching, you have given a plastic deformation to the material. So the main important thing is it is not applicable to elastic deformation, it is applicable to the plastic deformation. If the material is plastically deformed, for example, you are taking a rod and you are stretching it, once it is undergone the plastic deformation, what happens is after the plastic deformation, the material is already enlarged. So if you want to again compress the material, you have to first reduce whatever the enlargement you have given, then you have to reduce. For example, there is a rod of length 10 mm, so you have stretched it to 12 mm. Now if you want to compress it to 5 mm, so the ultimate you have to do is you have to reduce from 12 mm to 5 mm. So you need lot amount of energy, because previously it was only 10 mm, now it is 12 mm. So reduction of 12 mm to 5 mm will take lot amount of energy. So how this is happening? This is happening because of plastic deformation of a material, that is nothing but called as work hardening. When you give plastic deformation to material, it will have certain dislocation, that is nothing but in between the molecules there will be a space created. So with that arrangement, it will obtain some amount of energy in it. For example, again you can take the example of spring also. If you are compressing the spring, so because of compression, it will have some energy in it. When you leave the spring, it will give out all the energy. This is generally strain energy. So same thing, strain hardening. If the material is undergone some plastic deformation, then this kind of thing will be observed. So work hardening is very commonly employed both in pure metals and also on alloys, as because of improving the useful mechanical properties. So generally why we do this is we do this to improve the properties of the material, especially mechanical properties like strength and hardness of the material can be improved by doing the work hardening or strain hardening. Okay, what is the principle behind this is this we are going to discuss. When loaded, that is nothing but when we are going to give the a load to the workpiece, the strain energy increase. Strain means nothing but the deformation with the stress. So when you are applying the load with respect to the load, there will be a strain, there will be a deformation produced, that I will show you in the graph. Okay, if you see this is the graph. If I am applying the stress, because of stress in the initial condition, this condition is nothing but called as elastic condition, in which if you remove the stress, the material will regain its original nature. For example, if you take a rubber band, if you stretch a rubber band, the rubber band will stretch till its elastic limit. If you leave the rubber band, it will come back to its original nature. So after a certain limit, if you still keep on increasing the stress, so it will go beyond the elastic limit and it will go into the plastic deformation. So till here it is elastic region. After this point is generally called as yield point, where the material will be undergoing plastic deformation. So first what I am doing is I am giving the stress so that it enters into the plastic deformation, that is this limit A, where it is completely plastic deformed. So after reaching this point, what I am doing is I am removing the stress. So once you remove the stress and give the reverse of the stress which you have applied, so it will not follow the same graph, it will come down like this. So if you again improve the stress in positive direction, then it will follow this B, C, S3 and D curve. So if you give continuously without giving this break, which I have given at point A, so the maximum stress of that the material can withstand is this one, that we call as ultimate tensile strength. So this the strength of the material, if you are not giving any break, if you are continuously applying the stress, so this will be the maximum limit. So because I have given break here and I am leaving the material for certain duration, I am applying the reverse stress and again I am improving. So because of that, what is happening, that plastic deformation, when I am giving some break, the grain structure, whatever the material inside will rearrange themselves. Because of that, its strength will be improved. So if you see this gap S1 and S2, so S1 is the strength of the original material if you keep on applying a load at a continuous instant. Okay, S2 is the load, that is nothing but the ultimate tensile strength of the material if you are giving some break to the material and again you are applying the load. So this is called as work strain hardening graph. Okay, so the specimen is reloaded immediately. So if you want to read this, so if at the stage the specimen is unloaded, so that I am unloading, I am removing the stresses, the strain does not recover. The strain means the deformation will not recover. In elastic limits itself, the deformation will be recovered. But whereas if you do in plastic deformation, the same deformation will not be obtained once you remove the load. So it will not follow the path OA, but moves along the AB line. Instead of moving this OA line, it will follow the AB line. So because if the specimen is reloaded immediately, then what we have to do, once it comes down again, I am going to apply the load. The curve rises again from B to A, but via another path and reaches the point C, after which it follows the curvature if loading is continuous. If you are still applying the load continuously, it will follow the other path and it will go to the maximum that is here written. If the specimen would not have unloaded after a point A, means if we have not removed that stress, then the stress strain curve will have followed the path, dotted path AD dash. Okay, A D dash. Next, a compression of path ACD and AD dash shows that the cold working, that is nothing but plastic deformation, has increased its yield strength. Okay, yield strength is the point where the material will change its nature from elastic to plastic, and ultimate strength is nothing but the maximum strength which a material can withhold in its. Okay, after ultimate strength, the material will start breaking. That strength is called the ultimate maximum. Okay, next, how the stages of work hardening undergoes is, it happens in three stages. First, in the first stage, the whatever the dislocations are there, it will easily glide, means it will, because you are applying the stress, the deformation can be easily produced. For example, you take a material, if you are applying a load, with the application of load, the material will be expanding easily. So that is why we write it as easy gliding region. The next stage is linear hardening region. When already you have obtained the gliding easily has happened, so once you are, for example, if I give some initial of the topics or initial problems will be easy for you in any subject. So if you go deeper into the subject, you will feel little harder. So again, if I give large deeper problems, it will be much harder to you. Same as, so when you are applying the load initially, the material will seems to be easily deforming. So after a certain time, it will become somewhat hardened. So if you still want to hit at the same place, then it will become parabolic hardening region. So that we show as this case. So stage 1, stage 2 and stage 3. Okay, stage 1, this is a linear easy to glide stage. Uh, this is linear hardening and this is parabolic path. Okay, linear hardening means with respect to stress, there will be equal amount of strain generated. Okay, so easy gliding region. In easy gliding region, stress strain is almost constant. If you take out the relationship between stress and strain, it will be almost constant. For example, y is equal to mx. So m is constant. Y by x is will be always constant. Same as in this, stress and strain ratio will be always constant in easy gliding region because the material is purely elastic here. Okay, very low work hardening means it will have less amount of energy in it. So especially the BCC structure does not exhibit this kind of easy gliding region because the elements are present at the center and the corner. Next is linear hardening. Hardening rate is as high as as well as constant. To till some extent we have written it as a linear, so the hardening will be a constant as well as it will require large amount of energy. Whereas in parabolic low hardening, the material will become little harder, but the shape will be more parabolic. Okay, this the constant relationship between the shear stress and strain will not be there. So with the application of small amount of stress with stress, so the material will deform large amount with application of small stresses. In this case, in this region, if you apply small stress also, the material will undergo large amount of deformation because it has already crossed the certain limits of its nature. That is some ultimate strength, some yield strength that the plastic region has already reached. So in this region what happens means even if you apply small amount of load, the material can be easily breakable. So there is this kind of region will be parabolic region. So this effect was studied by a Washer effect which was discovered by Ohan in the year 1886. Okay, so this effect is a phenomenon in plastic flow. In most material, plastic deformation in one direction will affect subsequently the response in other direction. Means if you are, for example, if you are improving the length of the material, the diameter of the material will be reducing. If you take a rod or if you take a rubber band, if you stretch it, when the length of the rubber band increases, if you check its diameter or thickness, its thickness will be reducing. So in most materials, plastic deformation in one direction will affect the subsequent response in the other direction. So this phenomenon by which plastic deformation of metal increases the yield strength, that I have shown you how it is going to increase if you are giving some amount of break, that is nothing but in the direction of plastic deformation, and it is even decreasing the yield strength in opposite direction. This effect is known as Gaussian effect. Okay, so let us see this. So this is the graph of stress strain. So initially what you are doing is, this is the original graph. So if you see here, the material has yield stress in the tension as A. So this is the yield strength in tension A. Tension means positive direction. If you are applying in compression, that is in negative direction, this is my compression maximum for yield compression. Okay, so if a new specimen of same material is loaded in tension, pass the tensile yield strength to B, okay, along the path OAB, and then if it is unloaded, then it will follow this path. So once you are giving plastic deformation, what is happening means it will go through the elastic and it will reach the yield point. If this at this point, if you are applying the reverse stress, it will not follow this path because it has already crossed the elastic limit and entered into plastic region. So during the plastic region, what happens? It will not follow this path, it will directly come through this path. Again, I am applying the compression strength. If you still keep on improving, it will go here. Okay, OAB, and then it is unloaded, it will follow the path BC. So then follow the path BC. If now the specimen is subjected to reverse stress means previously you are giving tensile stress, now you are applying the compression stress. Okay, the plastic flow will begin at a stress corresponding to the load D. So at this point itself, it will undergo plastic deformation in reverse. Okay, in compression, which is apparently lower than the original compression yield. Original compression yield is your X, which I have written at the initial section itself. Okay, so thus while yield stress in tension was increased because of strain hardening, but whereas in compression it is being reduced from X to D. This phenomenon is called as Washinger effect. Okay, so Washinger effect is a reversible effect. If the specimen originally being stressed plastically, in compression the yield stress in tension would have been decreased. Okay, so this is again stress strain curve, which is again explaining the same thing. Now what is the conclusion with which we are going to see from Washinger effect is, metal forming operation results in a situation of exposing the metal workpiece to stresses of reversed sign. What does this mean is when you are trying to form the material, for example, I have given you the sheet metal example. So when you are applying the load on a sheet metal, one half of the sheet metal will be under compression, other half will be under compression. Okay, so the Bosnian effect contributes to work softening of the material. So if you keep on hitting the material in a sheet metal, what happens when the material will become soft and it will change its shape. For example, in straightening of drawn bars is nothing but if you are having a bar which you are reducing the thickness of the bar are rolled sheets just like your shutters. So where roller subjected to the workpiece to alternate bending strength. Alternate bending strength is nothing but first you apply positive bending, next negative bending, positive bending, negative bending. So because of that positive negative, its strength will be reduced and enable the greater cold drawing of the workpiece. Okay, so next is what is a cold working. What is cold working technically is it can be say defined as two terms. One is cold working, another is hot working. Hot working in which the metal will be heated to some temperature. Again we will try to make the material to undergo plastic deformation. Whereas in cold work we will not apply any kind of heat, and we with the repeated application of stress we will try to make the material to undergo plastic deformation. So in this plastic deformation, material temperature ranges from 0.3 to 0.5 tm. Tm is nothing but the melting temperature of the material. Okay, melting temperature of the material. So the material will be in this temperature itself. It will not be heated beyond this. So during cold working, the point defect densities will be improved. It will be increased. So it can be done. So when you are continuously doing cold working, the point defect densities will be improved. Because of point defects, the dislocations will be increased. Okay, which further makes the material stronger, but whereas the material will convert to brittle. So why it is converting to brittle is, so even though the strength of the material has increased, as it is having large number of dislocations, once the material start breaking, so the entire material will not undergo, already it has gone under plastic deformation, so further it will not go. Once you apply the stress, so it will be easily breaking. Okay, so the cold work material is harder but it is brittle. This has to be noted. This is the important point in cold working materials. Even though material will become hard, but whereas it will be brittle. So once it breaks means it will not undergo any plastic deformation. It will just like that break into pieces. So heating the material typically below zero point 0.5 temperature. 0.5 temperature is nothing but melting temperature of the material, and holding it for a sufficient time is nothing but you should not take the material once you heat, because if you heat the material, if you do the operation, it will be called as heat treatment or hot working operation. Whereas in this is a cold working. So typically it should be less than 0.5 m, and after heat treatment you should leave the material to some time, so that if a material is heated to some temperature and if you are leaving it, then that is called as annealing. Then it is called as annealing. Heating a material to certain temperature and leaving the material for certain duration, it is called as annealing. So if you are annealing a material, there will be changes in its recovery, how it is going to recover its structure, and because of the structure changes there will be recrystallization. The crystal structure we have studied, so the atoms in their crystal structure will try to rearrange themselves. Okay, that happens only at high temperature, whereas at low temperature it will try to recover. Okay. During this process, the material tends to go from microstructure, metastable state to the lower energy states. So the atoms inside will undergo from high level states to lower energy states. If you further anneal, that is nothing but if you are again heating and cooling it, so then what happens, because of this heating beyond zero point 0.5 temperature, the molecules or the crystals inside the material will try to arrange themselves. That is we call as recrystallization, and leads to the growth of the grain. That is nothing but the grain structure, which I have shown the grain boundaries, and the structure of the grains will be changed. One grain will flow from one part to the other side. Okay, So this is cold working. So after cold working, if you are annealing, the material will become soft.